Recording, okay. So, just as a reminder, pulsed ultrasound means exactly what it sounds like. It is pulses, pulse, 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 except it's happening at thousands of times a second. So, more like a machine gun than a BB gun. And we can have, get away from me, that's not what I wanted. We can have, on the other hand, continuous wave. We don't own currently, although that's actually one of the things I was just talking to Melissa about, is we have a grant, it's like a COVID grant, a little silver lining on the whole thing. So we're looking at things to purchase, and I mentioned maybe a continuous wave transducer, just one, so students could actually see what a continuous wave transducer does. It will put out a continuous wave, just non-stop. No picture though. Remember the whole how far away is the storm? Well, if it's continuously making noise, you cannot determine that. So with a continuous wave, no picture is possible. But on the other hand, we do get something in return. We can get a beautiful Doppler signal coming back. And so a Doppler shift coming back. So the sound is constant, therefore we can't create a picture because we don't know exactly where each echo came from. In fact, we don't even know really at all where the echoes come from. However, if you're aiming a continuous wave transducer at a vessel, you will get a shift coming back, and that can be read. So a continuous wave can produce a beautiful...
Are you trying to show us something?
Well, normally I would be sharing my screen, so yes. Shit. All right. I thought I was sharing screen earlier, but it must have... I'm just fixing you guys so I can see y'all a little better. Yeah, so crap. What I was showing you is, now you can see this now, right? My screen, I assume. Yeah, okay. So I first drew this as a continuous wave, my little CW for continuous wave there, and I put my little Doppler heading backwards to show that there is a Doppler shift is beautiful. And so what we can end up getting is not a picture. Let's see, a little smiley face. No, we can't get that, but we can get instead is a nice wave. Just like we already have, we have pulse wave. Continuous wave can produce that as well. In fact, it does a much better job than pulse wave does. Okay, but I'm getting a little ahead of myself. Really, all I really wanted to talk about is the fact that we have pulses of sound. And in this chapter, and then in the next chapter, we're really going to start breaking down those pulses. So we already broke down a wave. We look at the wavelength and the time and the period and all that stuff. We've started breaking that down. We're going to do the same thing going forward here. So get away. Okay, so once again, we have a pulse. This particular pulse is made up of 3 cycles. Doesn't always have to be 3. I want a prettier color. I always draw my pulses. I draw my pulses bigger at this end and smaller at that end. That is realistic. Unfortunately, that's not how the book does it. So I don't want you guys to get confused. The reason it's realistic is because this pulse starts off strong and then very quickly diminishes. And if we're going in that direction, well, that's the beginning. You know, this is the beginning. This is the high amplitude front of the pulse and the low amplitude weak end of the pulse. So that's just how I draw my pulses. Only pulsed ultrasound can create an image. We've already mentioned that. It is like a mild thunderstorm like we had last night. We had occasional lightning. And with that occasional lightning, good grief. With that occasional lightning, I would be able to say, oh, that was 2 miles away because it was a flash and then a sound. Continuous wave ultrasound is similar to a crazy thunderstorm where lightning, and sound. How far away is it? You don't know because it's basically a continuous wave of sound. Let's see, pulse duration and spatial pulse length. This is definitely review, so let me keep going a little quickly here. Pulse duration is going to be the beginning of the pulse to the end of the pulse. That's the time. And, oh gosh, well, this was in microseconds. I can't remember what the 0.3 to 2 microseconds. So 0.3 to 2.0 millionths of a second. Oh, that's right. Right there, duh. So let's just get rid of that since it's extra ugliness we don't need. The spatial pulse length is measured with the same 2 lines. This is similar to our lambda, our wavelength. And in fact, in this case, it'd be lambda plus lambda plus lambda equals the spatial pulse length. Or another way of saying it, 3 times the wavelength. Makes sense? That 0.1 to 1 millimeter. Smaller is better. We want this pulse to be really small. Smaller is better whenever possible. And so that's built right into the transducer, by the way. Not so much the machine, but the transducer itself creates that short pulse. We'll talk about that when we talk about construction of transducers. Pulse duration is by the sound source. In other words, just like I said, the transducer. Spatial pulse length, the sound source, because that source is going to determine whether it's 2 or 3 cycles long. But the medium for spatial pulse length, well, remember, wavelength is determined by the source and the medium. The source determines the frequency, which helps determine the wavelength, but also the wavelength is determined by how fast sound travels. The faster it travels, the more it stretches that sound out And so even though the frequency stays the same, the wavelength will actually change. So, so same thing, and we're talking about pulses, spatial pulse length is really the same thing as talking about wavelength, and that's determined by the sound source and the medium. Is this adjustable? No, we cannot adjust the speed of sound. It is what it is. And whether or not it is 3 or 4 or 2 cycles long, that's kind of built into the transducer. We really can't change that. There is an exception to that, but it's not worth talking about. But in the future, you might be like, but Mr. S, you said, I know, but. Oh, that's right. Yeah, Kurt says, meh, I don't know. That's it can be adjusted. And in fact, every time you use Doppler, it is adjusted. But I'm going to shut up. I'm not going to say anything more because don't want to disagree with the book. It does not help you guys. Echoes arrive back from depth equal to the pulse strip. I just have a note in here. I don't know, is this worth even mentioning right now? I guess if it's there. So if our pulse repetition frequency is equal to 1,000 hertz, 1 kilohertz, then our echoes return at 1,000 hertz. You put 1,000 sound beams, 1,000 sound pulses in, you're gonna per second, you're gonna get echoes coming back at a per second interval of the same amount. So 1,000 per second, or at least at that rate anyway. So let's see, we talked about pulse duration, spatial pulse length. Oh, and let's make sure that we remember that just like before when we were talking about period and frequency, pulse duration, and that's in microseconds, is equal to the number of cycles times period, but also I need more room. Because, all right, I'll just make more room here. Okay. So let's just write that again really quickly. Pulse duration is equal to the number of cycles times period. So remember, period is T. That's the period of one cycle. So on a continuous wave, the period is how long that happens. Pulse duration, number of cycles times period. Remember, back last chapter, period T in microseconds is equal to 1 over frequency in megahertz, microseconds. Microseconds and megahertz, remember, there are millions and millionths. they are mathematically equivalents. Remember, what this means when you have a product that is equal to 1 over, 1 over frequency is equal to period. 1 over period is equal to frequency. That means they are not just inversely related, they are actual reciprocals. It's a special form of inverse relationship. That was last chapter. Now this chapter, pulse duration is equal to number of cycles over frequency. These two equations are the same equation. This one and this one. I've just period is equal to 1 over frequency. So I've just replaced period with basically 1 over f, but since we're not talking about regular period, we're talking about pulse duration. 1 is actually number of cycles. So it was so much clearer in my head. I realize I might have messed you guys up a little bit here. It's actually clearer in my book too. Basically what I'm trying to say is let's erase some of this. Where's my little... I need more my tools here. Oh, I know. Edit. Image. I can't find it right now. It does not matter. Let's just erase this. Barely fits. Okay. Because in your book, on page 50, it has pulse duration, number of cycles, times period. And then it also has pulse duration, number of cycles over frequency. And what I was trying to show you, and I feel like I kind of confused the issue a little bit, is that when you go back one chapter and you realize that period and frequency are reciprocals, basically what we're saying here is pulse duration and cycles over frequency is basically the same thing. These are reciprocals as well, or it's the same type of thing. Yeah, just remember these two numbers. These are equivalent. That's all I'm saying. These are equivalent equations. Okay. I'm going to move forward because I don't think I've done you guys any favors right there. Okay. More about pulse duration. Okay, obviously, if you increase the number of pulses, your pulse duration, your spatial pulse length is increased. That makes sense. If you use a different frequency, either a higher frequency or a lower frequency, that's going to shorten or lengthen the spatial pulse length. We prefer to use few cycles and a high frequency, because a high frequency makes a smaller spatial pulse length. Doesn't always work for us. That's why we don't always use it. Spatial pulse length, pulse repetition period. Okay, so the pulse repetition period, I've mentioned before that this is a false picture here. We have two pulses at the same time. No, does not happen. One pulse goes out and all the echoes come back before the next pulse goes out. If you do not wait, and sometimes it can happen, we get an artifact. It's a range artifact, yeah. But in any case, this is a false picture, but we have to use this picture to kind of get things, to figure things out. Since I draw everything going in that direction, sorry, this is the way that. I end out with a little bit different image than your book, but it's okay. The beginning of one pulse, it's the beginning of the next pulse. So the pulse repetition period includes one pulse duration. In other words, talk time. It also includes one listen time as well. So listen, and remember last time, 99 or more than 99%, let's say 99.8% of the time, it is listening, and only 0.2% of the time is it talking. There are some other numbers in there that are just memorized numbers, the length, typical values. Is this adjustable? Yes, we adjust through depth measurement. Forget Doppler for right now, depth and depth alone. The deeper we go, the longer we listen, because we have to wait longer for all the echoes to come back. The more shallow, if we're looking at the carotid or thyroid, then the pulse repetition frequency is faster. If that is faster, that means we spend less time listening, more time talking, because it doesn't take very long for all those echoes to come back and our next pulse goes out. It's also called transmit time and receive time. So talking is transmit, receiving is listening. That kind of makes sense. Pulse repetition frequency. So yeah, pulse repetition frequency, pulse repetition period are perfect reciprocals of each other, just like in continuous wave, period and frequency are reciprocals. So there. Kind of going a little fast. I did want to slow down on duty factor though. This is kind of the point where I know we started to speak about this, but I looked at my notes this morning. I was like, or I looked at the book this morning. I was like, I think we need to slow her down here. Duty factor is really, let me move this again. It's telling us all about what we just talked about. So pulse repetition frequency and pulse repetition period have a mathematical relationship, and that relationship is simply called the duty factor, which I smile just a little bit every time I say it. That is percentage or fraction of the time that the system is on or talking. So I'm going to say, rather than percentage or fraction, I'm going to say ratio or percentage. I think ratio or percentage. In other words, if it's a ratio, it's going to be 0.01. And if it's a percentage, it's going to be, well, percentage, just all it means is times 100, right? That's how you have a small number or a large number, it doesn't matter. And you multiply it by 100, that's going to give you your percentage. Percentage. Okay. So in this case, we multiply by 100, we should be 0.1%. This is simply an example. So it could be shown either way. So therefore, no units. The reason why it's no units, by the way, it's because it's basically microseconds divided by microseconds. And they cancel out. Since they cancel out, no units are left. It is either simply a number or a percentage. Okay, typical values, clinical imaging duty factor ranges from 0.002 to 0.005. Oh, shoot. Tens, hundreds. Oh, that would be 1%. Okay, I did my math wrong, 1%. But typical values are 0.002 to 0.005 or times 100, 0.2 to 0.5%. Either way is fine. When creating these factors. So this is imaging. So basically what they're saying is let's just choose 0.005 or 0.05%. That refers to the pulse. The other 99.5%. So if this is 0.5%, listening time would necessarily be 99.5%. All right, because it's a ratio between the two. If this one's 0.5, this one has to be 99.5. Let's see, adjustable. Yes, it's adjustable. Just like above, simply changing our depth is all that we need to adjust this. The deeper we go, the lower the duty factor goes because the less time talking and more time listening. Turn by the sound source only. I have a little note, careful how I say this. But yeah, duty factor is inversely related to depth. Like that's just exactly what I just said. The deeper you go, the more time you have to listen, the less your duty factor will be. More about duty factor. And so duty factor. So, DF. I guess it should have been capital D. What does it matter? Doesn't matter. It probably doesn't matter. Duty factor percentage then is equal to the pulse duration, PD, divided by pulse repetition period. So pulse duration divided by the pulse repetition period. We don't need to have the listening time in the equation in order to figure out what the listening time would be. We just need the pulse repetition period, how many pulses in a second, and how long does that pulse last. So you divide those, you divide the PD by the PRP. Of course, multiply by 100 to get the percent, and that's going to give you whatever your number is. And so, do I have an example? Of course not. Okay. Typical values (0.2 to 0.5% for imaging. I mentioned at the beginning of class today that there are such things as continuous wave, go. Continuous wave transducers do exist. The pulse duration and the pulse repetition period are going to be one and the same. So you're basically going to get basically 100 divided by 100 times 100. You will end out getting 100%. In other words, the duty factor in a continuous wave, let's make sure we understand this is continuous wave, is 100% or 1. It's a ratio of 1 or it's a percentage of 100%. That's basically saying that it's simply always on or always talking or always transmitting. Oops, getting a little messy down there. Always on, always talking, always transmitting. That is what a continuous wave transducer does. Just so you know, on page 64, there's just a small mistake. And this is 64 Battleman, of course. It's parameters that describe both pulse waves and continuous waves, and it shows a kind of a nice little picture up top showing the difference between the two. Propagation, period, frequency, wavelength, and propagation speed. Pulse duration is not adjustable. Its units are in microseconds, determined by the source. Typical value is 0.5 to 3. The next one, pulse repetition period, is adjustable through depth. When we change our depth, we change our pulse repetition period. It's in milliseconds or thousandths of a second. Unfortunately, the typical value that they put on here is 0.1 to 1 millisecond. And on page 49, typical value 0.3 to 2. So I think think I told my last class I was going to look it up and try to find out which one's correct, and I probably never did. So I'll tell you guys the same thing. I'll try to figure out if page 49 or page 64 is correct on the pulse repetition period, typical values. But as of right now,
Page 49.
It's microseconds.
yeah, that's right. Microseconds. Oh, that's really off.
But it's also
That's double-
pulse duration. Not
Pulse
pulse
repetition period. Oh, wait a minute. Dang it, I got the wrong. All right, pulse repetition period.
You were looking at pulse duration in that period.
I know, but it's still, you know what? It's still diagnosed 100 microseconds to 1 millisecond. 100. Well, son of a bitch, that is correct. 100 microseconds is 0.1. Not only did I have the wrong page written down, in my book permanently, because I wrote right in my book, but when I get to the correct page, it's simply in microseconds to 1 millisecond. 1 millisecond, and this is milliseconds to millisecond. But 0.1 millisecond is 100 microseconds. All right, well. You blame Bree was here. She got out. I was going to say you could blame her. But,
You can blame whoever talking.
I'm still here.
you're still here. I don't see you. Oh. Oh, there you are. Oh, all right. It's all your fault, Bree. Oh, that's funny. I think it was your class. It actually might have been 2 classes earlier, but I don't know. Well, in any case, that little chart kind of helps figure out what is similar and what's different. Okay, so today, actually, I was thinking that I was going to do. So, how are you guys? Any particular questions on this chapter?
No, but you keep saying reviewing. When's our test? I have a test already made. The first test was 3 chapters. The second test. All right, let's see if I can look it up real quick. God, I'm like lost in my own computer here. Of course, it's not going to be there, is it? No. I know where it's going to be. Course tools. These are a lot of tests that you will not see, just a lot of questions, but don't worry, you won't be seeing all this. Test chapters 2 and 3. Edelman 12, 1 through 3, 4. This is for ending up for 4 and 5. Talk about 5 today. So the next test, as you can see, is chapters 4 and 5. So we're going to talk about 5 today. Today is Wednesday. That'll give us Friday to kind of think about that again. Probably Monday. So your eyebrows go up because we'll cruise through 5 pretty quickly. So that's 2 chapters down, and unless I make it another 3-chapter test, which I can make it a 3-chapter test and then put it off a little bit longer, or just keep it a 2-chapter test. And because then there's 6, 7, 8, 9. Oh, you're recording still. Oh, well. I am recording. Anyway. Yeah, so I think actually Monday is a good time, but we'll see. Okay, let me open up. Open recent. Do I want to save these changes? Sure. Okay. So we've talked about intensity in the sense of, we've talked about intensity in the sense of intensity is equal power divided by area. And that makes sense. So you don't have to change your power. If you change your area, you've changed the intensity. That's the flashlight against the wall analogy. You can change your focus and change the intensity in the middle versus spreading it out. The power doesn't change. Alternatively, yeah, we could take our power and turn our power up, and that will turn our intensity up as well. There's other ways of breaking down, especially the area, and then power. Another way of saying power is the amount of energy over time. So area and time, we're going to kind of take a look at. So in other words, spatial and temporal thoughts on intensity. Spatial refers to the distance or space in the average ultrasound beam. So the width of the beam itself is spatial. Temporal refers to in time, of course. So intensity during a pulse is going to be more than intensity during the entire pulse and listening time. And so we could be looking at temporal during the pulse, during the entire cycle of pulse to listen. So that will change. So spatial is, let me just put centimeter squared, in other words, area. What is your area? Temporal, I'm just going to put time. I didn't change the size of my pen, and I've seemed to have lost that. I've lost that capability, and I don't want to sit here and mess with finding it. Peak. Well, this is going to be peak. It's going to be maximum, of course. Max value. Average, well, an average is an average. The middle value. And then pulsed. That refers only to the transmit. So we'll put, these are just general terms, and then we're going to talk about what that all means. Well, I think, yeah. So what I have drawn here is my little transducer face here. And it's creating a beam of sound. Little misleading, but that's fine. For all we care about right now is that simply a beam is created. These beams are laser beams. If you could actually see the profile, you'd be astounded how the sound is manipulated to create a pencil lead wide region of sound. And if we were going to take a cross section of that beam, and I've taken a cross section right down in here, kind of at the natural focus point, so it's a little bit narrower right there. And I've taken that cross section and I've put it up here as a circle. In other words, we're looking straight down the barrel of the beam. You can imagine, just like a flashlight, unless you have a really good quality flashlight, most flashlights, when you look at them, the center of the flashlight has the strongest intensity. Now in ultrasound, the same thing happens. I don't even know what that is. And then along the outside, I don't know, let's just use this as a color. And along the outside, oh God, this is horrible. Let's just do this. I kind of shown it here. Kind of shown it? What language is that? Really? Highest intensity in the middle of the beam. And that's just the way it is. Just like a flashlight, tends to be higher in the middle, and then along the sides it tends to weaken a little bit. And then, of course, as you can imagine, along the outside, you have the lowest intensity. This is spatial. So spatial refers to location space. We experience this phenomenon in everyday life, certainly. The beam's intensity at the location where it is maximum is the spatial peak intensity. So spatial peak intensity is just referred to as intense. Screen's jumping all over the place. Intensity SP. That refers to spatial peak intensity. On this one is going to be dead center. And then there's no such thing as a spatial lowest intensity, so let's get rid of that guy. We have a spatial average, though. Intensity spatial average. And that is going to be, let's use a different color here, it's getting a little ugly. All the way across that, the highest intensities, the lowest intensities, all the way across is the average spatial peak average. So these are our first two values. When I say values, you're not going to have to work any of this out, which is good, because I don't want to work it out either. You have your intensity spatial peak, intensity spatial average. We're going to combine these spatial parameters with temporal parameters. These get a little more confusing. Okay, let's. I already wrote down spatial peak intensity, spatial average intensity down here as well. We have some others that I also wrote down. But let me use the picture here to draw them a little better. As one could probably guess, that is going to be intensity temporal peak. Remember now, everything, this is going to be temporal. In other words, in time, what is the peak? What's the peak energy in time? Okay, so let's go back to my green. Intensity I'm sorry, TP, temporal peak. Let's go ahead and write that real quick. Peak intensity. Of course, the beginning of the pulse, the highest amplitude of the pulse, that is the moment in time where you're going to have the strongest intensity. If you're following on page 71, I skip IM until the end. Intensity pulse average. So we have another one. Let's do a different color for each one of these. Intensity pulse average, IPA, which makes a good beer too. That is going to be the average of the entire pulse. So that might be along here. Maybe just a tad higher, but that's okay. So what, during the whole pulse, what is the average intensity of the sound there? By the way, all this is done, we don't, obviously we'll never do this again after this class, but this is done by bioethicists, by the federal government when they're looking at, they're testing whether or not an ultrasound system is going to cause damage to tissue or not. And they use these numbers to help them quantify that. Averaging the intensity during the entire pulse. That's a fun one. Let's do this color. Intensity. I'm sorry, and I just said the entire pulse. I mean the entire pulse and receive period. Averaging intensity during the entire pulse repetition period. So I don't want to say that wrong because we just did the intensity pulse. Temporal average, let's draw that part. Intensity, temporal average, and actually let's connect this one. This was pulse average up here. Let's see if I can replicate that color. This guy, I'm going to need to back off a little bit. Let's get it right about there. Temporal average. In other words, the average intensity, not just during the pulse, sorry, was it irrelevant distraction? Not not just during the pulse, which is pulse average, but during the entire pulse repetition period. So now, this average realistically is really low. We'll put it all the way down, almost at the baseline, because if you think about it, even though this pulse looks pretty strong, there's 99+% of the time we're listening. And so 99% of the time we're not putting any energy into it. So you could imagine that temporal average is 99% less than the pulse average. So this will be a temporal average will be a very small number. So spatial, oh, and then there's one other, yes. There's one more. It's kind of the oddball, and that's why I skipped it. If you're following along, I skipped it, and we'll go back to it right now, because it doesn't mix with the others. The other ones we're going to find out real soon that we're going to mix them all together. It's really fun. It's not. Actually, I don't like this chapter at all. I don't like talking about it. This one, let's give this a jarring color, red. Intensity M, or we could spell it out, or spell out max. Either way, IM or Imax. This is a little bit different because it's not only looking at peak intensity, that very moment of peak intensity, but what it does, it looks at the entire first half of the first cycle. In other words, not down there, only the first half of the first cycle and the energy involved in that. So I determine the average intensity during the most intense half cycle. So this is an average of first half of first cycle. So Imax, although it sounds rather masculine and scary, it's I'm IMAX, like a big movie theater, is actually that number, if we were to throw numbers on this, and we are not, but is actually a little bit less than temporal peak. Temporal peak is higher because it's only looking at the most high point period. And Imax is looking at the average of all the highest points, really, because it's in the first cycle. Okay, so then we'll be sure we'll review this. We'll review this because I'm sure some of you are just like your heads are spinning right now, but hopefully this is all making some sense. So, or at least when you go over it again, you'll be like, okay, I get it now. I get it now. So let's see, I have my temporal peak, my peak average, my temporal average, and the oddball Imax. And let's throw in the other one. Let's see, ISP and the IS. Let's throw these down here. We'll give that a nice blue. And then there's I, intensity spatial, peak, intensity spatial average. Spatial peak, remember that's the middle of the beam. Average is the average of the entire beam. Okay, now we're going to play with these. Fun. What the hell did I just do with those? Oh, my own hand was in the way. I couldn't see what was going on. Combining spatial and temporal factors for the study of bioeffects. In other words, these are the researchers. The intensity characteristics of sound must be described accurately with regard to both time and space. The following intensity measurements are used to describe the intensity of sound. Let's see, let's use a nice purpley color for you could do intensity, and we're going to combine these guys with these guys, and this guy's an oddball, so we're not going to combine him at all. So intensity, let's see, we always start with spatial. And what are we doing? We're going to start with the spatial. So we're going to say, let's start with this one first. So I, spatial peak. And then we're going to look at, well, this one. So we're going to combine those, spatial peak, temporal peak. Do a different color for each one, I guess. The next one they want to look at, I, spatial peak. So I, spatial peak. So they use the same one again down here, but instead they're going to look at pulse average. So SPPA. So let's see. That was the next one. Spatial peak pulse average. Then they look at intensity, spatial peak temporal average. Spatial. Oops. Let's get that. Spatial peak. For a third time in a row, we're using spatial peak. And we're going to say, but this time, temporal average. We use that one. And then finally, I could only assume that the last one we were going to, let's see, let's do a dark blue. Average, yep. Intensity, spatial average. So this time, finally, we're using the second guy, spatial average. That is the average. Spatial. I know I keep switching back and forth between capital letters and, sorry, that's just what I do. We're finally going to use the spatial average. Remember, that's the average all the way across the beam. Spatial average and temporal average, SATA. And then just don't put an N at the end because that's creepy. So temporal average, so that's this one, and then that average is used again. So there's actually other combinations are possible, right? But 1, 2, 3, 4, 5, 6, and that's only 4 of them. So there's 6 possible. I'm not going to write the other ones down. These are written down because these are actually used. The other possibilities are really not used. But if you want to know what the most dangerous part, the highest part of the beam in space and in time, you're going to look at this one, right? That is by far the That is the highest. Highest. It just doesn't look right. In every regard, it's the spatial peak. It's the middle of the beam and at the high point. So middle of the beam, and then over time, it's looking at the highest peak value. So combining these two, just funny looking, is that. Then you get spatial peak pulse average, and that's a little bit lower. Spatial peak temporal average, and that's lower still, considerably much more, because of temporal average and peak pulse average are very different numbers. And then you get the lowest possible. The average of the entire pulse, spatial average. So everything from the highest to the lowest to the temporal average. And so this is going to be the lowest of the useful reporting measurements. And then Imax is its own thing. I'm just going to read to you, and you guys don't have to write this down. It's right in your book. I'm going to pretty much read it word for word. Hint, for the boards, this is all you really need to know. So that's why I don't want to spend too much time on this chapter, because we could just read these 10. Intensities may be reported in various ways with respect to time and space. We just talked about that. Time, space, spatial, temporal. Different measurements of intensities are important in the study of bioeffects. The reason we do this, the reason somebody does this, not necessarily us, is to determine whether or not that little 4-week embryo is going to go or not. That's bioeffects. Spatial peak temporal average, ooh, let's write that one, is the most relevant intensity, and that kind of makes sense. Spatial peak, middle, spatial peak over time, over the constant time. So this is most relevant. Okay. The units are going to be in watts per centimeter squared, because it's an intensity. You have watts per centimeter squared. Because peak measurements are larger than average measurements, SPTP, intensity is the highest, and theta is the lowest. The number called the beam uniformity coefficient, bleh. It wasn't in the chapter, but it is in the review here, describes the spread of the beam in space. The SPSA factor is unitless with a factor greater than 1. Let me tell you about what that, it's really simple. All they're saying there, let's draw myself a little cross section of the beam. And then I'm going to need to fill that up with, intensity there, and let's just for the fun of it, it's not going to work. Okay, enough is enough of me. You guys don't need to watch me play. Right, the beam uniformity coefficient, SPSA factor. Let's go ahead and write that down somewhere. SPSA factor is a ratio. It is unitless. It doesn't, and it is simply how quickly or how much of a difference, how different peak intensity or spatial peak is from average. In other words, just how purple, that's not the right color, just how purple is it. Why'd you do this to me? Is this in the middle? Let's see, duty factor described. Interesting. I never noticed that before. Duty factor, which is not chapter 5, it's chapter 4, describes the relationship between beam intensities with time. The duty factor is unitless between 0 and 1, 0 being off, 1 being continuous wave. For continuous wave ultrasound, the beam is always on, and the pulse average and temporal average intensities are the same. Yeah, spatial peak temporal average, spatial peak pulse average would be the same because there are no pulses. So the pulse, it doesn't even make sense to even use those terminologies anymore. As spatial peak temporal, spatial peak pulse will be the same because there are no pulses. It just is what it is. And spatial average, temporal average, spatial average, peak average are the same. When pulsed and continuous wave sound beams have the same SPTP intensities, a continuous wave beam has a higher. When pulsed and continuous wave, spatial peak, temporal peak. Well, okay, so if you're following along, number 8, all that is saying is, of course, continuous wave is continuous. It's more energy. If you're going to get if you're going to mow down, I'm looking at a tree right now and I'm thinking machine gun. It's kind of weird. I don't know why, but if I wanted to mow down that tree with a machine gun, but I have it on semi-auto, bang, 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 it's going to take me all day, right? But if I have it on full auto and plenty of ammo, I could take the tree out because it's continuous, like a continuous wave. I don't know if that was a good example or not. Temporal considerations. We already talked about all that. We just talked about all that. I'm not going to repeat. Number 9, you can read it on your own. Number 10, what time is it? 11:30, we're okay. Spatial considerations, spatial peak intensity is maximum space. Yeah, we just talked about number 10 as well. I'm sure you guys have questions, but let's let you guys. It's Wednesday. Let's let you ruminate on those. Do these questions that are in the book, both in the chapter and the back. Always remember to do those. It's really important. Ruminate on this for a couple of days. Ask me questions on Friday, and we'll do some review on 4 and 5. And I think Monday, we'll be able to take a test on Monday, no problems. It's just like the last test, it's easy. I'll see you guys laughing. Okay, and then continue to move forward, chapter 6. Oh God, logarithm and decibel. So the first few pages of chapter 6, I really don't like because I have a hard time wrapping my head around why we do logarithm when it's really the same thing as exponential exponents, like 10 to the. it's the same difference as far as I'm concerned. But in any case, logarithm, decibels, I hate that part, but the rest of it, attenuation, I like attenuation, scattering, absorption, all that stuff. So, okay, cool. Most of 6 is a good chapter. It's just the first couple of pages. And if any of you guys are really good at math, actually, you could help me. I can talk to my daughter, I guess. She's smarter than I am. Anyway, I guess I'm done. I'm starting to ramble. Test on Monday, review on Friday. Oh, I've got a video. Let me post that for asynchronous assignment. Make sure you guys do that. I really need to stop recording at some point.